we have seen various photophysical aspects in photochemical reaction. We have explained those photophysical aspects using Jablonski diagram. Now, in this video, I will be explaining to you another concept, that is photosensitized reaction. Now, in photosensitized reaction, it is a photochemical reaction, but here an external molecule or a different molecule excites the reactant. It is not the reactant which is getting sensitized, or it is not the reactant which is absorbing the light or which is being sensitized by the light. It is another molecule which is called a donor. So, the in photosensitized reaction, an excited molecule supplies the energy to the reactant for the reaction to happen. This excited molecule is called donor. So, donor molecules are light sensitive, while the reactant will not be light sensitive. So, what in photosensitized reaction, the donor molecule will absorb the light, will take up the energy from the light radiation and then transfer that energy to the reactant, and from there the reactant will undergo reaction. So, this is also a photochemical reaction because it involves absorption of light energy, though it is not by the reactant, but by a different molecule, that is called the donor. And after the reaction, the donor is obtained back. There is no chemical change happening to the donor, there is only a physical change, that is, the donor gets excited, the energy of the donor is given to the reactant and the donor come down to the ground state. So, in photosensitized reaction, we have a photosensitizer. Photosensitizer is the one which we call as the donor, which is sensitized by the light. And this reaction is called photosensitization, or when the donor gets sensitized or when gets activated by absorbing light, it is called photosensitization. And once the photosensitization has happened, the reactant molecule absorbs energy from the donor and the reaction proceeds, and then we call it as a photosensitization reaction. Now, examples which act as donor molecules or photosensitizers are mercury, cadmium, zinc, xenon, benzophenone, organic dyes, etc. Now, these each sensitizer, each donor atom or each donor molecule will absorb energy of different wavelength, of different or absorb radiation of different energy, and it will transfer that energy to the various other molecules. So, when selecting a donor, we have to keep in mind what is the amount of energy required for the reaction to happen. We must keep in mind which type of donor will accept so much of energy and will release that much of energy to the reactant molecule. This reaction is very useful for when we go for green chemical reaction or the reactions which follow the green chemistry protocols. Now, examples for photosensitized reactions, we have conversion of molecular hydrogen to atomic hydrogen, that happens in the presence of mercury. Then we have conversion of cis-butene to trans-butene, happens in the presence of sulfur dioxide, and various other reactions. Photosynthesis is another photosensitization reaction, wherein the photosensitizer is chlorophyll. It is a chlorophyll which absorbs light energy and then transfers that light energy to water molecule to undergo photolysis. And then after that, various other reactions happens and carbohydrates are formed. And remember, not every donor molecule or every photosensitizer will carry out or will be useful to carry out every reaction. Each reaction has got its own sensitizer. So, mercury sensitizes or carries out reactions wherein molecular hydrogen is converted to atomic hydrogen, while cadmium transforms ethene to acetylene. Mercury again can go for the reaction of hydrogen and carbon monoxide to formaldehyde. So, all this, the photosensitized reaction and the donor, these two pairs depend upon the energy requirements of the reaction. Now, let us take one example, that is of hydrogen getting converted to molecular, atomic hydrogen. Now, before that, we shall go on to look into the Jablonski diagram of photosensitized reaction. Now, in Jablonski diagram, as we have the radiations, energy levels, this energy level which is on the left side of the slide or of the screen is for the donor atom or donor molecule or the photosensitizer. And we have the energy states or electronic states of the acceptor molecule or the reactant. Now, when you irradiate light, the donor gets excited, it gets excited and goes to higher energy state, and from there it comes down to lower energy state via vibrational relaxation or internal conversion. All those radiative transition, non-radiative transitions are possible. Now, once it has got come down to the lowest vibrational level of the first excited state, it will undergo intersystem crossing and go to the triplet state. Now, from the triplet state again it undergoes vibrational relaxation, and from the lowest vibrational level of triplet state it goes to the ground state, singlet ground state. Now, when this happens, when this relaxation mode happens, that is movement of the donor species from the lowest vibrational level of triplet state to the lowest vibrational level of singlet state, energy is emitted. That emitted energy is taken up by the acceptor molecule. That is how the energy is transferred by the donor to the acceptor. So, it is not the acceptor which is getting excited by light radiation, it is the donor which is getting excited. And the donor goes to excited state, comes down to ground state with a release of energy, and that energy is accepted by the acceptor molecule or by the reactant, and you get back the donor, the D is obtained. So, D to D star and then D star to D is obtained, and then the acceptor gets excited, it goes to higher energy level and then product is formed. So, the first step, D is getting converted to D star, and the second step, D star or the excited donor transfers its energy to the acceptor molecule or the reactant, and A gets forms A star, and then A star is getting converted to the product P. So, the energy from the light radiation is transferred to the reactant via a donor atom, a photosensitive molecule or a photosensitive species. So, this is the Jablonski diagram for photosensitized reaction. And when we look at the dissociation of molecular hydrogen into atomic hydrogen, what happens? You have mercury, which is the photosensitizer there or the donor atom, donor species. Mercury gets excited by absorption of light, and then the excited mercury transfers the energy to hydrogen molecule. Now, why do we need this donor? It is because hydrogen does not have the capacity to absorb light of that a particular energy. So, hydrogen takes the help of mercury, or we take the help of mercury to make hydrogen excited. Now, we can carry out the same by thermal radiation, by thermal reaction, but if this is done by photochemically, then we can save energy, and then we will be following the green chemistry protocols. Now, once the hydrogen molecule has got excited, it then breaks down to hydrogen atoms or atomic hydrogen. So, you are getting back the mercury in the second step. In the first step, mercury is going to excited state, while the second step, mercury is brought back to the ground metallic mercury. So, you can retain or regenerate the donor molecule, and you can use it again and again. It is not wasted, or it is not converted to any other species. Now, when we talk about photosensitization, we need to understand or we need to know about quantum yield of a photochemical reaction. Now, in photosensitization, the donor molecule or the donor species accepts or absorbs light energy and then gets transfers it to the reactant, and then the reactant gets converted to product. So, how much of energy has been used up, be it in a photosensitized reaction or be it in a normal photochemical reaction, is all the energy which has been absorbed from the light is being transformed to chemical energy. We need to know that. Now, that the quantitative analysis or the kinetics of photochemical reaction is done using the information from quantum yield. Now, to understand quantum yield, we need to know what is a photochemical reaction. We know already that we have the primary process and the secondary process. Primary process, the molecule gets excited, and in the secondary process, the molecule gets converted to the excited molecule gets converted to the product. Now, this photochemical reaction is governed by two laws of photochemistry. They are the Grotthuss-Draper law or the first law of photochemistry, and then Stark-Einstein law or the second law of photochemistry. Now, it is these two laws which govern the kinetics of photochemical reaction or the rate of the photochemical reaction. Now, we shall see each law, just a brief look at each law. Now, in Grotthuss-Draper law, it is also called as principle of photochemical activation. It states that only those radiations which are absorbed by a system can bring about a photochemical change. So, for a photochemical change to happen, light energy has to be absorbed. That is what the Grotthuss-Draper law says. But remember, not all the light radiation which has been absorbed will result in a photochemical reaction. That means, the converse of the Grotthuss-Draper law is not true. Remember, for a photochemical reaction to happen, absorption of light is necessary, and also remember that when a light absorption happens, it need not result in a photochemical reaction. There must be energy, the energy for the reaction and the energy absorbed must be equivalent or is required. Now, the Stark-Einstein law is also called as a principle of quantum activation or photochemical equivalence law or photoequivalence law. Now, this law quantifies the energy. Now, what this law says is that every photon that is absorbed will cause a chemical or physical reaction, and each molecule which is getting excited by the light in a photochemical process absorbs one quantum of energy or one quantum of the radiation. So, those energy or those radiations which result in chemical reactions, okay, that energy is transferred completely to the molecule, and that quantity is given as E is equal to the quantity, the energy is quantified as E is equal to n0 h nu, where h is the Planck's constant, nu is the frequency. And remember, this law, both Grotthuss-Draper law and Stark-Einstein law, these two laws are applicable only to primary process. That is because it is the primary process which involves light absorbance. Secondary process does not require light. It is only the primary process, that is the reactant getting converted to the excited molecule, which requires light. And if it is in the case of photosensitized reaction, it is a donor which is getting excited, which needs light, and the rest of the reaction does not need light. Now, with this background, we can discuss about quantum yield or quantum efficiency of a photochemical reaction. Now, that is designated as phi. Now, phi is a ratio of the number of molecules reacting in a given time to the number of quanta of radiation absorbed in the same time span. So, when some amount of light is being given to a molecule or to the reactants, how much of the reactants are getting converted to the product, or how much of the reactants are reacting. That ratio gives the quantum yield. Now, the number of molecules of the light absorbing substance undergoing reaction per quantum of radiation absorbed. Now, the quantum yield can be 1, that is the ideal case. When we say phi is equal to 1, equal number of molecules gets converted to the product, equal number of radiation, this equivalent radiation is absorbed. So, when such a reaction happens, it strictly obeys the Stark-Einstein law or the photochemical equivalence law. And a very good example for a reaction wherein phi is equal to 1 is the conversion of SO2 and sulfur dioxide and chlorine to SO2Cl2, wherein whatever amount of light has been absorbed, whatever energy of light has been absorbed is completely converted to chemical energy. There is no wastage of energy. Now, we have most of the reactions have phi less than 1 or phi greater than 1. And this case appears when primary process is followed by a secondary process. That is, after excitation there is a secondary process, and this secondary process or after excitation, not all the energy has been transferred to the reactant for the formation of product. Some of the energy may be lost in the form of heat or in the form of radiation, fluorescence, phosphorescence, etc. We shall see that. Now, let us look at the photochemical reaction with high quantum yield, that is wherein phi is greater than 1. Now, a very good example for this reaction is conversion of hydrogen and chlorine to HCl in the presence of light. Now, here we have the phi value is 10 to the power of 4 to 10 to the power of 6, very high quantum yield. That means the yield, the reaction is quite fast and the yield is quite high. You need to give only a very little of energy and you get a lot of product. Now, this reaction happens via chain reaction. Remember, almost all the photochemical reaction happens via chain reaction. That means it will be having 3 steps: chain initiation step, chain propagation step and chain termination step. The chain initiation step is will be the primary process which requires light. The other two, propagation and termination, does not require light, it happens on its own. They are the secondary processes. Now, in this case, the chain initiation step is absorption of light by chlorine molecule. So, in this reaction, it is chlorine molecule which is being sensitized. Now, this is what I had told in an earlier video, wherein the photochemical reaction involves selective activation. So, even though there is hydrogen and chlorine, only chlorine gets activated. And earlier when I talked about photosensitized reaction, I said for for hydrogen to get activated, you need a donor. That is why you use mercury, and then hydrogen gets activated and then it forms atomic hydrogen. So, hydrogen is not a photosensitive molecule. Now, here chlorine gets excited, it forms chlorine free radical, the bond between 2 chlorine atoms breaks, lyophilic, there will be each electron will move on to the chlorine and you get chlorine free radical. And then chain propagation step occurs wherein the chlorine free radical reacts with hydrogen and forms HCl and hydrogen free radical. And the hydrogen free radical again combines with chlorine to form HCl and chlorine free radical, and this reaction can continue. Once the hydrogen free radical is generated, it can react with chlorine, or once the chlorine free radical is generated, it can again react with hydrogen. So, in both the steps, that is in both the cases of this chain propagation step, a free radical is evolved which results in the formation of the product. And here termination is possible, wherein the 2 free radicals, hydrogen free radical and chlorine free radical, can form the product HCl, or 2 hydrogen free radicals can combine to form hydrogen molecule, or the 2 chlorine free radicals can combine to form chlorine molecule. So, here the secondary process promotes the consumption of more reactant molecules. That is why the yield of this reaction is very high. The product formation is very high. So, hence we have high quantum yield. So, the reasons for very high quantum yield, we can have 4 reasons, you may be having more reasons. Now, the 4 main reasons are: the photoactivated molecule may initiate a series of thermal reaction. So, once the molecule gets excited, the rest of the reaction follows, the secondary process follows. And it can also be the heat evolved in a secondary exothermic reaction may activate other molecules. So, the secondary process, if it is an exothermic reaction, it will also result in the activation of molecules. There will be thermal activation of the rest of the molecules. And then the photoactivated molecule may activate other reactants through collisions. That is also possible, that is energy transfer is happening. And finally, an intermediate product formed may act as a catalyst, that is also possible. The free radical which is formed, or the intermediate reactant or species which is formed, may act as a catalyst. Because of all these reasons, the reaction can have good quantum yield. Now, let us consider another reaction wherein the quantum yield is very low. Let us see what are the reasons for that, and very good example is formation of HBr. Earlier we saw formation of HCl, here we are seeing what is the problem with formation of HBr. Now, here also we have hydrogen, we have bromine, in the presence of light HBr is formed, but the quantum yield is only 0.01. In the case of formation of HCl, it was 10 to the power of 4 to 10 to the power of 6. Here it is only 0.01, less than 1. Now, this also follows chain reaction mechanism with 3 steps: initiation step, propagation step, and chain termination step. Now, in the chain initiation step, we know hydrogen is not photosensitive, halogens are. So, bromine gets sensitized and gets converted to bromine free radical. And then this bromine free radical can react with hydrogen molecule and form HBr and hydrogen free radical. And this reaction is endothermic, that means it absorbs heat energy. It is not emitting energy, or it is not giving energy to the surrounding, it is taking up the energy from the surrounding. Now, this point is very important, please keep it in mind. This conversion of formation of HBr by the reaction of bromine free radical with hydrogen is an endothermic process. And another possibility is that the hydrogen free radical formed reacts with bromine molecule to form HBr and bromine free radical. Now, the formed hydrogen free radical can combine with the HBr, that is a product, and form hydrogen molecule and bromine free radical. And in the termination step, the 2 bromine molecules can combine to form, bromine free radical can combine to form bromine molecule. Now, why is that the quantum yield low here? Now, look at the first chain propagation step, which is endothermic. So, in the early case, when we were discussing about the reasons for high quantum yield, we said one of the reasons which we said was there will be thermal energy is being transferred to the rest of the molecules. Now, here that is not possible, because the energy, the heat present in the system is taken up for the reaction to happen, for the product formation. HBr is a product. So, when we talk about yield, we need to know what is the amount of HBr formed. Now, here the when HBr is formed, it takes up energy, heat energy. So, the rest of the molecules may not get excited. Secondly, look at the third step in the propagation step. The formed product is again used up and we get back the reactant. So, there is no formation of product, reactant is brought back. So, the yield becomes low. So, it is these 2 steps, the first step of the propagation and the third step, case of the propagation, which brings down the quantum yield. Alright, since the propagation step is an endothermic reaction, and during the propagation step, if the product is used up, then the yield comes down. So, the reasons you can list out the reasons. The photoactivated molecules may undergo quick non-radiative deactivation, that is possible. Another reason is photoactivated molecule may undergo radiative deactivation through fluorescence or phosphorescence. So, if that also happens, the energy is lost. It will not get converted to the product, it will come down to the reactant. So, if energy is used up for fluorescence or phosphorescence, the product will not be formed. Another reason, some of the photoactivated molecules may undergo reactions other than the desired one, that is, certain other side reactions may happen. Product formation may not happen, undesired reactions can happen, as in the case HBr is again converted to Br free radical and H free radical or hydrogen molecule. Now, the primary photoactivation step may be reversed, that is, product is getting converted to reactants, and some of the reactions leading to the product may be energetically unfavorable, resulting in reverse reaction. So, energetically it will not be favorable. So, reverse reaction, that is, formation of reactant may happen, we will not get the product. So, these are the reasons why we have low quantum yield, or why certain photochemical reactions have low quantum yield, and such reactions are not advisable or are not preferred when compared to certain reaction which has high quantum yield. So, production of HCl photochemically is favored, but production of HBr photochemically is not, because the quantum yield for the production of HBr is low. So, these are the things which I intended to discuss with you under the topic of photochemistry. All right. So, we have discussed Jablonski diagram, how it is used to explain various photophysical process. We have used Jablonski diagram to explain photosensitized reactions, and we have also seen the kinetic part of photochemical reaction by explaining the quantum yield of a photochemical reaction. Thank you.